The art gallery problem is one of the classical problems in geometric optimization. Given a polygonal region, place as few stationary guards as possible, such that the entire region is guarded. One could save personnel by using a single mobile guard. Then the objective is to find a tour that illuminates the whole gallery. Surprisingly, this problem can be solved efficiently if the gallery is a simple polygon. Now let's consider searching with incomplete information. Here is a hungry cow living on a line. If she knew that her hay is to the left, she could simply go there. But as she doesn't, her best strategy is to walk back and forth, each time doubling the search distance until she finds the hay. This way, her path will never be longer than 9 times the optimal path. The worst-case ratio of what an online strategy achieves without information over the optimal solution with full information is called the competitive ratio. If a mobile guard has to explore all of an unknown region, he has to dynamically plan a tour along which he will eventually see any point in the region. For a simple polygon, a competitive factor of 26.5 can be achieved. A crucial step in online exploration is the question of how to look around a corner. Given an initial position at a wall and a known distance to the corner, how should one move in order to see a hidden object or the other part of the wall as quickly as possible? Going straight for the corner may turn out to be a bad choice if the object is visible by a small step to the side. On the other hand, the total length of the curve determines its performance in case the object is only visible from there. More generally, we have to compare for any possible position of the object the length of the curve until the first point that sees the object with the length of a chord to the semicircle to the corner. In this manner, following the semicircle yields a ratio of pi over 2, or 1.57. Balancing the ratio of curve length and chord length yields a differential equation that can be solved numerically. The resulting curve is shown here. The optimal competitive ratio is 1.21. Developed at Fraunhofer AIS, Kurt 3D is an autonomous robot that is commercially available. A Pentium 3 notebook and a C167 microcontroller drive the robot. 2 90-watt motors are used to power the 6 wheels. Front and rear wheels have no tread pattern to enhance rotating. Here we use a controlled velocity of about 1 meter per second. Traveled distance is measured by odometry and scanner. A fundamental problem in the design of autonomous mobile cognitive systems is the perception of the environment. Kurt is equipped with a fast and reliable 3D laser scanner. The 3D scanner is built on the basis of a custom 2D rangefinder. The laser scans the environment horizontally and vertically with a precision of 1 centimeter. It detects all objects, even the cameraman taking the scene. From the scanned 3D data, a virtual environment is built. Thus, Kurt can plan trajectories and locate objects, for instance a chair at a corner or door. Each time a robot surveys its environment, it has to stop and perform a scan. The time for this procedure is in the order of several seconds, but can be adjusted at the expense of resolution. As we will see, accounting for scan times has a serious impact on the online problem. In the following, we will measure distance traveled by the number of scans that could be performed. If the distance to the corner is 1 scan, then going there will incur a competitive ratio of 2 if the object is right behind the corner. On the other hand, performing more than 1 intermediate scan will cause the ratio to be at least 2 if the object can be seen from the corner. If we use precisely 1 intermediate scan, we can get a better result. By considering a point on the semicircle and balancing the respective ratios, we get a competitive ratio of 1.84. Considering any intermediate position leads to a more complex nonlinear optimization problem. The optimal ratio is 1.81, only slightly better. Let's increase the distance by reducing the scan time. Local optimality forces the performance ratio to be constant at all times. Let's fix it to some value and consider scans on the semicircle. For an optimal scan position just beyond reach, we get a new step length. This can be iterated. If the process reaches the corner, then the competitive ratio can be achieved. The whole recursion can be evaluated by a few lines of C code. In the case shown, the result is still close to the optimum with a ratio near 2.12. As it turns out, the competitive ratio tends to 2 for even larger distances. There is a matching lower bound for all strategies, so ours is asymptotically optimal. The following shows a scene at Berlinghoven Palace. Kurt starts in a corner, about 8 meters from a door, with a chair behind it. In the first scenario, Kurt starts at 1 scan from the door. After detecting the door, he heads for the intermediate scan point. From there, he takes a scan, then turns towards the door. Depending on the position of the chair, he can either get to it directly or he has to perform a second scan. For the second scenario, we shorten scan time, so the distance to the door is 2 scans. Here are the resulting step lengths in meters. Now Kurt rolls towards the second scan point. Now it's time to head for the exit. See you later, Kurt.